Hello, my name is Josh Arfin, and I'm a junior math major from Lafayette College. This summer, I was lucky enough to work through the Excel summer program at Lafayette College with Professor Trent Gogler on our project, Stochastic Reweighting Schemes and Empirical Investigation. This summer, we worked on what are called U-statistics. U-statistics are a very general and simple class of statistics that includes many commonly used statistics, such as sample mean, sample variance, and sample covariance. The fact that they are such a simple class of statistics, such a general class of statistics, amplifies the importance of finding out information about them. A degree K statistic, defined by the kernel h of data point of x1, x2, all the way to xk, is of the form given in the first white box. Now, what this means is that we look at a function of some number of data points, k for a degree k kernel, and we sum all the possible interactions between them and divide by the number of interactions to get an average for each statistic. Specifically, we study U-statistics with degree 1 and degree 2 kernels. Degree 1 kernels are fairly simple, where we just are looking at a function of a single data point, whereas degree 2, we look at a function of 2 data points. So for example, sample variance is xi minus xj squared, and you sum that across all xi and xj pairs. The standard bootstrap is a tool that we use in statistics in order to learn something about the distribution we're studying. For example, if you look at the first plot, we see 15 data points pulled from a standard normal distribution. This does not look normal in any way. But when we randomly pulled 15 data points with replacement from that set of 15 data points we found, we did this 10,000 times, and you can see the second plot is exactly what a normal distribution looks like. So we were able to recreate the distribution the data came from this very non-normal looking set of data. What we look at in this project is what's called the stochastic bootstrap. So instead of randomly pulling from the 15 data points, we reweight the 15 data points randomly from some distribution, such as Poisson, exponential, or chi-squared. One of these is called the data-dependent weights, or Guilleau weights, which is from a French mathematician named Guilleau, who develops a set of data-dependent weights where we estimate the first 4 moments of the distribution of the data in order to create a distribution for the weights. The specifics that we will look at today are, there's 2 kinds. There is IID weights, so independent, identically distributed. The weights don't care about what the other weights are. And then we have non-IID weights, where we divide the mean of the weights in order to make sure that the average stays near 1. The average of the weights is 1. Now, we looked at 4 different distributions: normal, exponential, Poisson, and left skew, which is just a negative exponential distribution, to see what weighting schemes would work well for each of these 4 types of distributions of the data. What we found was that in every case, for a less than alternative, the Guilleau weights were incredibly effective with very low level and reasonably high power. What we found was that for not equal to alternatives, or for greater than alternatives, the non-IID Poisson weights and the standard bootstrap were the most effective for exponential, left skew, and Poisson data. For normal data, the t-test just was the best. So what we found was that for means, the non-IID weights, the non-IID Poisson weights worked very effectively for non-normal data, but for normal data, t-test was still the best. Now we're going to continue this research, and we are looking at extending this to use statistics with kernel degree 2, such as variance, and we want to write a package that allows easy implementation of our weights. Our future study would look at more degree 2 kernels and kernels that are more complicated. Thank you very much, and I hope you enjoyed this presentation.